Let's build a random forest model in Python to help you better understand how it works. Today, we'll be building a random forest classification model to predict whether a bank customer will default on their loan within the next month. We'll be working with this Kaggle dataset where each row is a past customer and the columns capture things like their age, credit limit, payment history, and past bill amounts. Our goal is to use these features to predict whether a future customer will default on their payment next month, so we treat each classification as a simple will default versus will not default. A random forest is a great fit for this type of problem because it's really good at picking up nonlinear patterns and interactions between features and is much more stable than trusting a single decision tree. If you want a slower, more detailed explanation of how a random forest itself works under the hood, then make sure to go back and watch part 1 of this video. But for now, let's get coding. As always, we must start by importing all of our libraries. We're using pandas to work with data, and all of these tools from scikit-learn as our machine learning toolbox. They'll help us split the data, train the model, and evaluate it. And now it's time to actually load in the data. We're reading it in as a CSV and saving it as our official data frame. Now we define our target and features in the dataset. Here, the matrix X contains only the features that the model is allowed to ask questions about, such as balances, age, and past payment behavior. And the vector Y contains the thing we want to predict, which is whether each customer defaulted next month. At this point, we are simply telling the model what columns describe the customer and what column carries the label. We take all of our data and split it into two camps: training data and testing data. Training data, which is defined as xtrain and ytrain, are the customers the forest will see while it's building the forest, deciding the splits, and choosing how to label leaves. The test sets, xtest and ytest, are kept completely hidden during this learning process. We will use the testing data after the model has already been trained to check how well it performs on unseen data. And this train test split is the basic safeguard against us fooling ourselves. If the forest looks really good on the training data but fails on the testing data, then all of the fancy tree building has just memorized the past instead of learning patterns that will carry over into the future. This is the step where our theoretical description of a random forest turns into an actual model. When we create this random forest classifier with the estimator is equal to 100 and fit it on the training data, we make the library repeat the decision tree building process 100 different times. For each individual tree, we draw a new bootstrap sample to be used as the training data for that tree. This basically means that we pick rows from the original dataset at random with replacement and let that sample be the tree's full private view of the world. And as the tree grows and looks for splits, the max features parameter forces each node to only consider a random subset of the features. And inside each tree, the mechanisms are exactly what would happen with a standard decision tree with that randomness built in. It starts with all of the sampled customers in one impure group, repeatedly asks yes or no questions to reduce the impurity in the subgroups, and leaves us with a set of leaf nodes at the very end of the tree. All of these leaf nodes correspond to a specific type of customer, and the model figures out whether that type of customer is likely to default or not. And each one did so using a slightly different subset of customers and features. The forest exists to blend all of these slightly different views, so you rely on the average behavior of many trees instead of trusting one singular fragile tree. Once the forest has finally been trained, we turn to the inputs of the testing data and ask the model to make predictions. For each and every single row in xtest, the model sends that customer through all 100 decision trees. Each tree walks the customer down its own series of splits and outputs its own classification for that customer. The forest then averages those probabilities across all the trees to get predict_proba and turns that into a hard class label by essentially letting all of the trees vote. By comparing those probabilities and labels to the true outcomes in ytest, we see how this averaging and random forest performs on genuinely new customers. Finally, let's zoom into one specific customer so you can see what this means in practice. This new customer is treated just like someone walking into the bank today with a new application. Their features are sent into the forest, and each and every single tree contributes its opinion on how likely someone with that profile is likely to default. The forest averages all of those probabilities into default prob, which is the model's estimated chance that the customer will default next month. In the real world, this is the number that the bank would plug into some decision rule. For example, if the probability is above a certain threshold, the bank might consider denying that credit line. Then it turns that into default label, which will output a hard classification of will default or will not default based on how the trees voted. So this one line of output is where all the abstract ideas about random feature subsets and averaging across trees collapse into a single concrete decision about a customer's risk. Now let's look at the outputs. The ROC AUC came out around 0.75, which means the model is pretty good at ranking risky customers above safe ones, but there's obviously a lot of room to grow. And the classification report backs that up, so we'd call this a good but not amazing baseline. And for that single customer we tested, the probability that they would default was around 19%, so the model predicted they would not default on their loan next month. Finally, we've plotted a feature importance plot with matplotlib just for fun, and it shows that the most recent payment status, or pay_0, is by far the most important signal in predicting a customer's risk. And that's a random forest model coded out for you in Python right in front of your eyes. If you learned something from this video, then don't forget to save it for later and follow for more.